Good morning, dear students. Today we're good morning, dear students. Today we are having this 18th practical lesson, so pre-ultimate lesson in this semester. And this practical lesson is about power series. So there are different kinds of series in math. So on previous lesson we were solving tasks with uh, numeric series, and today we will work with uh, power series that look like this. So un, so coefficients un multiplied by xn, by x in power of n. So this is the generic form of power series. So let's start investigating power series for convergence. So we will have to determine the region of convergence of power series. So starting investigating the following series. So n from 1 to infinity, x in power of n over n square. So how to determine the regional convergence of such series? First of all, we have to find the radius of convergence. In this case, we will use a formula similar to Downbred test, but the fraction is turned over. So in a Downbred test for convergence of numeric series, we use so un plus 1 is in the numerator and un is in the denominator, but here is vice versa. So what we will divide? So 1 over n square and 1 over n square, oh, n plus 1 square. And it will be equal 1. So series converges for all x that for all x from segment from interval -1, 1. And now we have to well, on which moment I stopped. So did you see this?
No.
And
we stopped when you started calculating of the limit.
Okay, so I calculated this limit, found the radius of convergence, and from this formula we can see that power series converges for this interval, so x from -1 to 1. And now we have to investigate the behavior of the power series on edges of this interval. So what about x equal -1? So we'll substitute -1 here, and we will receive the numeric series that has alternating signs. And let's look at the series that is formed by modules of these values. So this is a generalized harmonic series, that has power of p equal to 2, that is greater than 1, so this series converges. This numeric series converges. So for x equals -1, power series is convergent. And what about x equal to 1? We will have actually the same harmonic, so generalized harmonic series, but it will be only positive signed series, and it converges as well. So this series converges absolutely. So for x equals 1, the power series converges. So finally, we will conclude that this power series converges for x from 1 to -1 inclusively. So this is the region of convergence. Any questions about this exercise?
Can you go down? And
Yeah.
no questions.
Anybody else? Okay, if no questions, let's go next. So the next exercise 1b. So n from 1 to infinity, n factorial by x in power of n. So again, calculating the radius of convergence. So substituting the terms. So n factorial and n plus 1 factorial. So after I cancel n factorial, I will receive 1 over n plus 1, and it will be equal 0. So what does it mean? That this power series converges only at one point. So only one point, x equals 0. So that's the partial case. Any questions?
No questions.
Okay, no questions, so let's go next. Having the following series. Okay, so moving to 1c. So again, n from 1 to infinity. -1 in power over n. X in power of n. And over n in power of n. How to find the radius of convergence here? We will use the formula that is similar to radical Cauchy test, but it will be, so again, inverse value. So a radical Cauchy test looks like this. Oh no, module is inside of the root, actually. So for radical Cauchy test, this root is in the numerator, but in this case, it's in the denominator. So, having the following situation. So 1 over n in power of n, it will be actually equal to limit of n when n approaches infinity, and it will be equal infinity. So it means that this series converges everywhere. For infinite, so for infinite radius of convergence, it converges everywhere. So for all real x. Any questions?
No questions.
No.
Okay, if no questions, let's move to the next exercise. So having the following series, so n minus power of n minus 1, n multiplied by 2 in power of n, and x plus 2 in power of n. So now we don't know when it converges. And first of all, let's calculate the radius of convergence. In this case, we will use, again, a D'Alembert test. Stop, un in the numerator over un plus 1. So 1 over n over by 2 in power of n, and in the denominator n plus 1 and 2 in power of n plus 1. So n and n plus 1 will be cancelled because they are equivalent on infinity. Then we will cancel n. So actually we will receive 2. So this series converges for x from okay, let me write down and then I will explain. From x for x from -4 to 0 exclusively. Why do we have such non-symmetric region of convergence? Because we have a shift, so this shift. So x minus minus 2. So we have to add this shift to both edges of the interval. So, and we receive -4, 0. So any questions about this case?
No.
Okay, if no questions, so let's continue investigating. So for x equals -4. So when x equals -4, let's write down the series. So here will be -4. So different levels. So -2 in power of n. Okay, and it will be -1 in power of n, and 2 in power of n. And now let's simplify this series. So 2 in power of n will be cancelled. here I will have -1 in power of 2n minus 1, so it will be equal -1 always. And I will move minus out of the sum. What can we say about such series? This is a harmonic series that divergent, or that is always divergent. So at x equals -4, the series, power series diverges. And now what about x equals equal to 0? So, by the way, it's 1D. So substituting 0, and let's see what we will receive. So 2 in power of n. So after simplifying, we will receive the following series. So we will receive alternating series, and we will use the Leibniz test for it. So and reminding you Leibniz test. So first of all, I need to check the following condition. So the module of un, so limit of module of un must be equal to 0. So 1 over n, and it equals 0. So the first condition is met. Then un plus 1 equals 1 over n plus 1, and it is less than 1 over n. So less than 1 over n, and it equals, so that equals un. So this series converges according to the Leibniz test, and it converges conditionally because so the series formed with the modules is a harmonic series that diverges. So it converges conditionally, but even if the numeric series in such case converges conditionally, so now we conclude that the power series converges at this point. So it doesn't matter if it converges conditionally or absolutely. So now we will sum up that this series converges for x from -4 exclusively to 0 inclusively. So this is the final answer. Any questions about this exercise?
No questions.
Okay.
Can you go down a bit?
Yeah.
I probably no questions.
Okay. If no questions, let's move next. So to the exercise 2, and we will have to calculate the sums of power series with using term-by-term integration and differentiation. So how to solve it? Let me first of all write down the series, and after that I will explain it to you. So -1 in power of n by x in power of 2n plus 1 and over 2n plus 1. and modulo of x is less than 1. That's important. So how to solve it? What actually? So how to find the sum? What does it mean in this case? So sum of the series actually is a function. So we need to find the elementary function which will represent the sum of this series. So now let's differentiate this series. So now we will use term-by-term differentiation, and let's see what we will receive. And then, so we differentiate this. So each term will be differentiated. So we will receive the following stuff. So x in power of 2n and 2n plus, so we will receive the following series. And now let's write down it. Let's write down it's like a usual sum. So first a few terms. So term number 0, so will be equal to 1. Then term number 1, x in power of 2. Then the third term will be x in power. It was the first, and it so 0 first, second. So the second x in power of 4 minus x in power of 6, and so on. We have the following a series that is actually looks like a geometric progression, and it's actually a geometric progression that infinitely decreases because modulo of x is less than 1, so we can write it like sum of the geometric series. So so the first term is 1, and the denominator is minus x. So 1 minus x, 1 plus x squared. So we wrote the derivative of this series as an elementary function, and now we have to write down the sum. So we need to integrate this sum. So how to integrate? So we'll again use term-by-term integration. So from 0 to x. And here I will substitute t instead of x. And now let's move integrate under the sum sign. So we will receive the following stuff. But of course, we will not integrate this. We will integrate the elementary function that we received for x, so for the derivative. So we will integrate this expression. And as you remember the table of integrals, it will be arctangents of t with substitutions from 0 to 1. Oh, from 0 to x, sorry. And it will be actually arctangents of x. And that's the sum of this series. So we wrote it as elementary function. Any questions about this exercise?
No.
Okay. Then let's move next. 1b. Oh, so sorry, 2b. Okay, I will leave this part. So having the following series. So n from 1 to infinity. X in power of n over n. So actually this is the sum of this. So let's write this series as a sum. And again, now we will differentiate it. So we will receive x in power of n minus 1, and n will be eliminated. And now writing down this series. So what I will receive? So substituting 1. So 1 plus x square plus x cube plus x in power of 4 and so on. And again, as x module of x is less than 1, we can write it like a sum of infinite geometry, so like a sum of geometric series. So the first member is 1 and the denominator is x. So we have the following sum. And how to integrate it? So how to find it? We will integrate this function. So from 0 to x, dt over 1 minus t. So we will receive such logarithm of 1 minus x. So why I don't write the module? Because so module of x is less than 1, so the argument of logarithm is always positive. So if I substitute x, I will receive minus logarithm over 1 minus x, and if I substitute 0, I receive 0. So it will be minus logarithm of 1 minus x. Any questions about this exercise? Yeah, and always don't lose this condition. So any questions?
No questions.
Okay, no questions. And now we will use, so we will solve the inverse task. So we will expand the given functions into Maclaurin series. So in the previous task, we wrote down the functions as series, so series as elementary functions, and here will be we will expand the function into the series. Let me remind you how the Maclaurin series does look like. So k from 0 to infinity, and f, so the derivative over the order of k from at point 0 multiplied by x in power of k and divided by k factorial. This is the expanded form. Okay, I will write down here that it is Maclaurin series. Okay, so we will expand the following function. F from x equals sine square of x. There are two ways how to solve this task, but so the first way we will just look it through, and we will use the second one. So the first way is to calculate derivatives of this function. So here calculated 5 derivatives at point 0 and found that so the rule that the nth derivative equals the following expression. So 2 in power of n minus 1 sine of 2x plus n minus 1 multiplied by p over 2. So this is the method of solution based on the definition of Maclaurin series, and then just substituting values that received here. And what about the second way? We will use, so first of all we will rewrite our function. So we will use we will reduce the power. So 1 minus cosine of 2x. So it will be 1 plus 1 over 2 minus 1 over 2 cosine over 2x. And we will use the standard expansion of cosine of x. Let me write it down here. So cosine of x will be expanded into the following series. So n equals 0, so n from 0 to infinity, and minus 1 in power of n, and x in power of 2n over 2n factorial. So only even powers, and x belongs to real numbers, so any real number. So let's use this formula. So cosine of 2x will be equal, I will just substitute 2x here. So 2x. So 2x in power of 2n. Let me expand it. So 2 in power of n, of 2n, and x in power of 2n over n factorial. And now substituting this value into this, so into the function f from x. So 1 over 2 minus 1 over 2, and this series. And now I will simplify it a little bit. So simplifying 2. So removing this. So and here I will receive 2n minus 1. Then what about this minus 1 in power of n? I will also do the following stuff. So 1, okay, yeah, so plus here and n plus 1. So 1 stop. So 1 over 2, and here will be n plus 1. Let me check with the answer. Oh, I see. Here I also used moved out of the sum the first, so the 0 term. So the 0 term will be minus 1 over 2. So if I substitute n here, so if I substitute 0, minus 1 over 2, and then plus this sum, but starting from index 1. So the final answer is the following. Any questions about this exercise? Okay, if no questions, let's move to the exercise 4. So actually, this task, so B and C are analogically, so they will be for your home task. You will use a standard method of, so you will use standard expansion. And for this function, first of all, you will have to expand it, so to rewrite it like a sum of elementary fractions. And moving to task number 4. So here we will have to expand the function into a Taylor series. So Taylor series is actually the generalization of Maclaurin series. So how Taylor series looks like? So we can actually, so we will do the following. So expand by power of any, so at any point, so point x0, and how it's written, x minus x0 in power of k. And here will be not 0, but x0. And if I substitute 0 here, I receive Maclaurin series. So Maclaurin is the partial case. And in task number 4, we have to expand the function into Taylor series by powers x minus 2. So how to do it? First of all, we will use the formula of standard expansion, and so the following expansion, 1 over 1 minus x. So n from 0 to infinity x in power of n. Yeah, and modulo of x is less than 1. We will transform a function f from x to the form similar to it. So what is important for us? It's important to receive 1 here, to transform 1 in, to transform 4 into 1 with different arithmetical operations. And here and x must be transformed to x minus 4. So 1 over 4 minus x minus 2 plus 2. And then we will receive, so after expanding brackets, we will receive 1 over 2 minus x minus 2. So done with the transforming x. But we also need to transform 2. And how we will do it? So I will just move 2 out of brackets, out of denominator. So 1 over, so here will be 1 and minus x minus 2 over 2. So it is okay. It's important to receive 1 here. And then we will substitute it into this formula. So x will be substituted into this formula. So 1 over 2. So substituting this into here. So x minus 2 in power of n and over 2 in power of n. So this is their final answer. Okay, let's also move 2 into this series. So 2 over 2 in power of n. And also we have to write down that this expression, so modulo of this expression, is less than 1. Or we can also multiply by 2, and we will receive a modulo of x minus 2 is less than 2. Any questions about this exercise?
No.
Okay, if no questions, let's solve one more exercise, and after that we will have a break. So the task is related. So now we starting using so application of power series. So we will calculate the limit. How we will do it? So okay, first of all, let me write it down. So x approaches 0. So 2e in power of x minus 2 minus 2x minus x square, and in the denominator x minus sine of x. And we have the undetermined form 0 over 0. Actually, we can easily eliminate it with using L'Hospital rule, but the requirement is to use Maclaurin series. So how we will do it? Let us use the standard expansions. So e in power of x equals so the following. So we will have the following expansion. So n from 0 to infinity, and it will be equal x in power of n over n factorial. And what about sine of x? Again, we will also expand it. So sine of x will be equal the following series, so n from 0 to infinity, and here we will have odd powers, so minus 1 in power of n, x in power over 2 n plus 1 over 2n plus 1 factorial. So the following stuff. Then what we will do next? So next we will substitute these formulas into this limit. So what about e in power of x? So 2, and here which powers I have? So 1 plus x plus x square over 2 factorial plus x cube over 3 factorial, and let's write down one more term, plus x in power of 4 over 4 factorial, and so on. And here minus 2 minus 2x minus x square. And what about the denominator? X minus, so the following stuff will be, so substituting 0, I will receive x minus x cube in power over, so x cube over 3 factorial plus x in power of 5 by 5 factorial, and minus x in power over 7 over 7 factorial, and so on. So it's enough. And now let's expand brackets. So what I will receive? So 2 plus 2x plus x square plus 2 plus 2x cube over 3 factorial plus 2x in power of 4 over 4 factorial, and so on. and minus this stuff. And here again, as well, expanding brackets, and here just changing signs. So 2 will be eliminated, 2x and x square eliminated as well. And what about the denominator? X will be eliminated. So moving next. So undeterminate form so is still not closed. But what do we have here? So we can reduce it by x cube. So 2, here will be x, 1, x square, x in power of 4. And now we can, so we will substitute 0 instead of x, and we will receive, and we will receive 2. So here 2 over 3 factorial, and here 1 over 3 factorial. Any questions about this exercise?
No.
Okay, if no questions, let's have a break, and after that we will continue solving tasks related to application of power series. So 5 minutes. Let's continue. So the next task, task number 6, and we will use Maclaurin series to calculate different values approximately with accuracy 0.001. So we will calculate sine of 18 degrees. And sine of 18 degrees actually will be rewritten as sine of p over p over 10. So turning it to radians to form that already, so that we already know, and how to calculate it. So we will use this standard expansion of sine of x. So I will substitute p over 10 into this formula, and now let's write down a few terms. So the first term, so substituting 0 here, and I will have p over 10. So that's the first member, then minus substituting 1. So p cube over 10 cube, and 2n factorial plus 1, it will be equal, so we will have 3 factorial, so multiplied by 3 factorial plus, so substituting 2, p in power of 5 over 10 in power of 5, and multiplied by 5 factorial. And let's write down one more term. So p in power over 7 over 10 in power of 7 multiplied by 7 factorial. And so on. So what we have to do here? So we will calculate each so module of each of this term, and until it will be less than required accuracy. So let's do it. So p over 10 equals so p over 10 is less than required accuracy. So continue. Oh no, so it's greater. So continuing calculating. What about this value? So p cube over 10 cube multiplied by 3 factorial. Again, it is greater than 0.001, and calculating the next term. And this term is less, so module of this term is less than required accuracy. Okay, let's also write down the value that approximate value. So no, so 0, 100, 0.314. Here 0.005, and here 0.4 zeros 26, and it is less. So to calculate this value approximately, so we will use only these two terms. So we will use some of these terms. And approximately it will be equal the following value. So P over 10 minus this value. And we received 0. So here we received 0.309. And now let's calculate it in online calculator. Yeah, so actually, so calculated here. By the way, so how calculated such functions as sine, cosine, exponent, and so on in programming languages, actually with using power series. So that's one of examples. So what next? Number E. Okay, let's just look through this exercise. So we have the following series, and to simplify the work, we just evaluate the nth remainder of the series. So remainder looks like this, and it is less than 1 over n factorial by n. And after substituting n, substituting n equals 6, such inequality is true. So the module of remainder is so meets the requirement of accuracy. And after calculating the series, after calculating, received the following approximate value. Any questions about 2C or 2B?
No questions.
Okay, if no questions, let's move to not to 6C, and we will use expansion. So we will use power series to calculate integrals. So we will have to calculate the following integral that you know that we cannot calculate it with the standard method of integration. So no differential entry, integration by parts. That's not table integral. And you actually know from theory of probability that this integral is similar to Euler. So it is Euler-Poisson integral, and you know it from theory of probability from normal distribution. So it's similar to it. So how to calculate it? So we will use the standard expansion over exponent. But we will substitute minus x in power of 2. So replacing exponent with this series, and here will be minus 2x squared in power of n. And then let's expand it a little bit. So minus 1 in power of n. And multiplied by 2 in power of n, and x in power of 2n. So received the following value, and now we use term-by-term integration. So what we will have here, okay, let's write down the antiderivative. So -1 in power of n, 2 in power of n, x in power of 2n plus 1 over n factorial by n plus 1. 2n plus 1, sorry. So received the following series, and with the substitutions from 0 to 1 over 3. Let's substitute. So if I substitute 1 over 3, I will receive the following stuff. Okay. Now let's stop. Okay, it would be better. So here will be 1 over 3. And if I substitute 0, I will receive 0. Okay, so now how it looks like. So let's simplify it a little bit. So let's rewrite it into a convenient form. So 2 in power of n, and here will be 3 in power of 2n plus 1. Let me check with my notes. So x in power of, stop. Stop. Y minus 2x. Yeah, really. Mistake. It mustn't be here. Yeah, so something was wrong. And now it should be correct. Okay, so writing down the first terms. So when substituting 0, so 1 over 3 minus 1 over 3 by 3 in power of 3. Then plus 1 over 2 factorial, so 2 by 5 by 3 in power of 5 minus 1 over 3 factorial by 7 and by 3 in power of 7. I guess it would be enough. If not, we will calculate more. So now let's evaluate these expressions. So 1 over 3 definitely is greater than required accuracy. And what about 1 over 81? So let's calculate it here. So 0. So approximately 0.012. So it's greater than required accuracy. And now let's calculate module of the next element of the next term. So 1 over 3 factorial by 7, by 5, stop, 2 by 5 by 3 in power over 5. And it's less than required accuracy. So it equals approximately 0.00041. It's less than 0.001. So it will be enough for us to calculate only these two values. So this integral equals approximately these values. And let's calculate. So 1 over 3 minus 1 over 81, it equals about 0.321. So this value. And now let's check with the computer mathematics systems. So for example, Wolfram Alpha, that we already know. I guess you already know it. So let's integrate. So from 0 to 1 over 3 dx. Yeah, and it's actually, so this value matches. Any questions about this exercise?
Could you explain how 2, 1 plus n in denominator appears in the second row? Yes.
Yeah. So here we have x in power of 2n. So we integrate it and we receive here x in power of 2n plus 1. And
Okay, thank you.
yeah, so just it's just a table integral. More questions?
No questions.
Okay, if no questions, let's solve one more exercise related to application of power series. So we will use the power series to integrate differential equations. So we will have the following equation: y prime twice equals xy prime plus y, and y from 0 equals 0, and y prime from 0 equals 1. We have to write down first three terms, first three non-zero terms of the series, expansion of the solution. So such a differential equation cannot be solved analytically. So there are no formulas to solve it. Yeah, actually, this is a linear equation with variable coefficients, so not constant coefficients, but variables, and not all of them can have exact solution, like this equation, for example. And to write down the solution, we also need to have initial conditions. So we will solve this Cauchy problem approximately. So how to do it? So we need to find, so we will use this Maclaurin series, and we need to find first terms, first three terms. We already have one non-zero term for this, so for y prime, and now we have to calculate next derivatives at point 0. So y prime twice at point 0 will be equal the following value. So I just substitute values here. So 0 by 1 plus 0, so it equals 0. Then we will find the third derivative. The third derivative is the following, so we just differentiate both parts. So y prime plus x y prime twice plus y prime. Let's simplify it. So x y prime twice plus 2y prime. And calculating the third derivative at point 0. So xy prime twice equals 0 and 2y prime equals 2. So found the third derivative. Let's move to the fourth derivative. Let's calculate it. So again, differentiating this equation. So y prime twice plus xy triple prime plus 2y prime twice. So what I have xy prime 3 times plus 3y prime twice. And y, so the fourth derivative of y equals, so at point 0 equals 0. So if I substitute here, so when x is 0, this value is 0 as well, so we have the 0 term. And now let's find the fifth derivative. So it equals y prime 3 times plus x y, so the fourth derivative, and plus 3y prime 3 times. Simplifying it a little bit. What's going on? Okay. So wrote it down. Then what do we have? So we will write down there. So let's calculate the derivative at this point. So the fifth derivative at point 0 equals equals 8. So we have already three first non-zero terms. So y prime from 0 equals 1. So the third derivative equals 2, and the fifth derivative equals 8. So let's write down it into the Maclaurin series. So y equals the following stuff. So writing down just first terms. So now x, okay, so x over 1 factorial. Okay, let's do like this even. 1 over 1 factorial x plus plus 2 over 3 factorial x cube plus 8 plus 8 over 5 factorial x over 5, and so on. Let's also simplify it. So x plus 1 over 3x cube and plus okay, 5 factorial 112, so 8 over 120. 8 over 120 is 1 over 15. So 1 over 15 x in power of 5, and so on. So actually done with it. And by the way, let us try to find the rule for this derivatives, finding these derivatives. So for example, the nth derivative, how it will look like. So so the nth derivative, so looking at these first derivatives, so xy prime plus y. So what do we actually have? So x y in so and derivative of n minus first order and plus n minus 1 y, so derivative of of y of n minus second order. So let's, for example, substitute, so substituting 2 here, and it's actually true. So substituting 3. So yeah, so here will be the second derivative, here will be coefficient 2, and here the first derivative. Substituting 4, actually the same. So actually we can use even this value somehow. So yn at power, so the nth derivative at 0, so I'm actually not sure how it will look like, but actually that's it. Any questions about this exercise?
Can you go down for the last calculation?
Yeah.
No, no more questions.
Okay. By the way, we also have some time to solve exercise B, so let's do it. So we have the following differential equation. One more interesting example. So y prime equals x square plus y cube, and y prime from 1 equals minus 1. Y from 1 equals minus 1. So here we have the first order. Okay, so let's find let's calculate these terms. So y prime from minus 1 from 1 will be equal. So actually 1 minus 1. So it will be equal 0. And now let's calculate the second derivative. So the second derivative will be equal to x plus 3y square by y prime. And so the second derivative at point 1 will be equal, so substitute, so 2, yeah, it will be equal to, because y prime from 1 equals 0. Then calculating the third derivative. So it will be equal to plus 3 plus 6y and y prime over y prime square multiplied by y prime square plus 3y square by y prime twice. So received this expression. So this y prime will be equal 0. Okay, so calculating the value of this derivative at point 1. So what it will be? So 2 plus 0 and plus So 1 by plus 3 by 2, so plus 6, it will be equal 8. So calculated the first terms. So first 3 terms, this, this, and this. And in this case, we will use not Maclaurin series, but Taylor series, because we have point -1. So approximate solution will be the following. So -1 over so -1 the zero derivative just will be -1. So yeah, so here here will be 0 point, so just -1, and then it will be 0, and after that plus 2 over 2 factorial x minus x plus 1 square. And what about the third derivative, 8 over 3 factorial by x plus 1 cube, and so on. And if I if I simplify it a little bit, what I will receive, -1 plus x plus 1 square plus so 8 over 3 factorial, so 8 over 6, so 4 over 3 plus 4 over 3 x plus 1 in power of 3, and so on. Any questions about this exercise? About the whole lesson? About previous lessons?
No questions.
Okay, if no questions, let's finish. Have a nice day. Stay safe. Thank you for your attention. Goodbye.
Can I ask a question
Goodbye.
Yes, of course.
about individual home task?
Mhm.
I mean,
Yeah. So do you want to get answer individually? Okay.
yes.
Okay. So maybe.
I mean, yeah, I wanted to ask